Hello, this video is about the electromagnetic spectrum and calculations for determining wavelength, frequency, and energy. Okay, so before we can get to the calculations, you need to understand what the electromagnetic spectrum is. And it is this, and there's several different ways that you can find this represented online and in textbooks. But it's basically a classification of the different types of electromagnetic radiation. And electromagnetic radiation is a way that energy flows through space. And it can be X-rays when you have an X-ray done to check to see if you have a broken bone, or at the dentist's office. It can be UV light from the sun. The visible spectrum is the part that we can see with our eyes. Infrared, microwaves, radio waves. So anytime you tune into a radio station, all you're doing is changing your tuner to the particular frequency that the radio station is broadcasting on, and then long waves. And short waves are in here too for shortwave radios. And so the visible light spectrum is white light. It's what we see when we see white light. And when you pass white light through a prism, it shows the rainbow of colors because it's separating out all the colors. So white light is made up from all the colors of the rainbow. All right, and so it's basically all of this is light. The only part we can see, though, is the visible spectrum. So, excuse me, light then can travel by waves, right? Light travels in waves. And so if we look at a wave, okay, what we call the distance from one peak to another peak is called a wavelength. And wavelength is represented by the Greek letter lambda, and it's typically measured in meters. We'll often report visible light in nanometers, or you might see micrometers sometimes, but for the most part it's measured in meters. And then we also have something called frequency. And so if I draw another wave down here, this one has a higher frequency because it's happening more frequently in the same amount of time. So I'm going to move these up a little bit, and I'll write that down here. So we have the word frequency. And frequency is represented by the Greek letter nu. Some places you'll see it represented by the letter F, but if you look in any college textbook or AP book, it's usually represented by the letter nu. And it's measured in inverse seconds, or hertz. And they're the exact same unit, just preference of how it's reported. And so frequency is basically how many times the wave cycles in a given amount of time. And that's why we call it per seconds, or inverse seconds right here, is because this wave cycles so many times per second. And then the last term that you need to know about is energy. And energy is represented by the letter E, and it's measured in joules, and that's abbreviated with the letter J. And so if we go back and we look at the waves here, this one with the higher frequency has a much higher energy because it's moving more, and this one has a lower energy and a lower frequency but a much longer wavelength. And so what we can get from that is wavelength and energy have an inverse relationship, meaning that if one is high, the other one is low, and vice versa. And also, wavelength and frequency have an inverse relationship. But energy and frequency have a direct relationship. So if one goes up, the other one goes up. And so there's a way to mathematically connect these three, and that's what we're going to talk about, and I'm going to solve some problems so that you guys can see some examples. All right, so the relationship between wavelength and frequency is what I want to talk about first. So we have wavelength and frequency. And the equation that we use for those two is wavelength times the frequency is equal to the speed of light, c. And so this is the speed of light. And all electromagnetic radiation travels at the speed of light. So it's all traveling at this speed. And its value is 2.998 times 10 to the 8th meters per second. All right, and so the next relationship that I want to talk about is the one between energy and frequency. And so this one is the energy is equal to H times the frequency. And in this case, energy is measured in joules, and H is Planck's constant. Oops. And Planck's constant is the number that was found to represent, to be multiplied by the frequency to get the energy for one photon. And so one particle of light, you would calculate the energy of that one particle of light at a particular frequency using H. And the value for H is 6.626 times 10 to the negative 34 joule times a second. And so you can see, looking at both of these right here, that it's very important to have the right units, because if you don't use meters for wavelength and you don't use inverse seconds for frequency, you're not going to cancel out the right units here in the speed of light. So wavelength always has to be in meters when you use this equation with this value for C. And frequency always needs to be in inverse seconds. And then the same down here for this equation, energy always has to be in joules when you use this equation with this value for H, and frequency always has to be in inverse seconds. So if it's in any other unit, you have to change it before you put it into the equation. All right, and then there's one more, and it is between energy and wavelength. And so if we look at these two right here, we look at these two equations, I can come up with a relationship between energy and wavelength by substituting in what frequency is up here, and frequency would be equal to C divided by the wavelength. So to give you the equation, it's going to be E is equal to H times C divided by the wavelength. And so the same as using these, your H's are going to be the same because it's a constant. The speed of light is going to be the same because it's constant. And so you have to make sure that your wavelength is in meters and your energy is in joules. All right, so this problem says UV radiation has a frequency of 6.8 times 10 to the 15th inverse seconds. Calculate the energy in joules of the photon. So before we do that, I want to look at the equations over here on the right side, and I'm going to pick the one that has what I'm looking for and what I've got in it. So the question says ultraviolet radiation has a frequency of 6.8 times 10 to the 15th inverse seconds. So I have frequency, right? And I want energy. So I'm going to have to use the equation. I'm going to have to use this equation because it has both energy, which is what I'm looking for, and it also has frequency in it. So I'm going to write out energy is equal to, and then H is the 6.626 times 10 to the negative 34 joule seconds. And then frequency is 6.8 times 10 to the 15th inverse seconds. And so when I take a look at this, seconds cancels out and I'm left with joules. So now I just have to put this into a calculator and get my answer out. And what I end up getting as my answer is 4.5 times 10 to the negative 18. And as for sig figs, I was given 2 sig figs in my problem right here, and so I'm going to keep 2 significant figures in my answer. And the unit left over is joules, and I was looking for energy in joules. And so that's it. All right, so in this one, I'm going to have to do the same thing. And so I'm going to look at this, and I've got one electron transition. One of the electron transitions in a hydrogen atom produces infrared light with a wavelength of 7.464 times 10 to the negative 6. What amount of energy causes this transition? So I've got 7.4 times 10 to the negative 6 meters, and that's the wavelength. And I'm looking for energy. And so this time I'm going to have to use this equation, right? Because that equation has energy in it and it has wavelength in it. And so it has what I want, the energy, and it has what I have. So if I plug those into the equation, I'm looking for energy. My H is 6.626 times 10 to the negative 34 joule times a second. And then my C, speed of light, is 2.998 times 10 to the 8th meters per second. And then I'm going to divide that by my wavelength of 7.464 times 10 to the negative 6. And that's in meters. And so again, if I check my units, seconds cancel, meters cancel, and so I'm left with joules, which is what I want to find. And so I'm going to multiply this out and divide. So I'm going to multiply this times this, and then divide by that number. And what I end up getting for my answer is 2.661 times 10 to the negative 20 joules. And so that's the correct answer for that one. All right, and then in this next problem, it's going to be a little bit different. What we have is we want to know what the wavelength is in nanometers this time. So we want to know what the wavelength is in nanometers, and we're looking for a frequency in hertz. And we have an energy equal to 1.4 times 10 to the 24th, negative 24th kilojoules. And so I'm going to find the frequency first. And so in order to find the frequency from the energy, I'm going to have to use this one, because it has energy in it, and that's what I have, right? It has energy in it, and I want frequency. So I've got an energy of 1.4 times 10 to the negative 24 kilojoules. Now remember, in this equation, this is in joules, so I have to have my energy in joules. So I have to convert it from kilojoules to joules first. And there are 1,000 joules in 1 kilojoule. And so my energy is going to be equal to 1.4 times 10 to the negative 24 kilojoules. And then 1 kilojoule is 1,000 joules. And so my energy is equal to 1.4, times 10 to the negative 21 joules. And so that's the number that I'm going to use when I plug it into this equation, because it's in joules, not kilojoules. So I'm going to put it in there as 1.4 times 10 to the negative 21 joules, and that's going to be equal to 6.626 times 10 to the negative 34 times my frequency. And so to solve for frequency, I'm going to use the exact same way we do it in algebra, and I have to isolate my variable. And so looking for this as my variable, I'm going to divide both sides by 6.626 times 10 to the negative 34. Joule seconds. Those are the units for H. And so this cancels out over here, right? And then we have joules cancel out right here. And so the unit that we end up with is inverse seconds. And so I put that into my calculator, the 1.4 times 10 to the negative 21 divided by 6.626 times 10 to the negative 34. And what I end up getting is 2.1 times 10 to the 12. So the frequency is equal to 2.1 times 10 to the 12th inverse seconds, or hertz. It's the same thing. All right, so now we have frequency, and we have to find wavelength. And so in order to do that, I can either use this equation right here with the energy value that was given to me in the problem, or I can use this equation right here. I'm going to use this one because I haven't used it yet. So I know that I need wavelength, and I have frequency from the last question. And so I'm just going to use that frequency and plug it in right here, and then solve for wavelength. I'm going to move everything up. And the equation that I'm going to use, I'm just going to rewrite it over here, is the wavelength times the frequency is equal to the speed of light. So C is it's 2.998 times 10 to the 8th meters per second. And so I'm going to use my frequency right here and plug it in right here, and then use C right here. So I'm looking for wavelength, and frequency is 2.1 times 10 to the 12th inverse seconds, and then the speed of light is 2.998 times 10 to the 8th meters per second. And if I need to solve for this variable, then that means I'm going to divide both sides by this number. So dividing by 2.1 times 10 to the 12th inverse seconds. Then my units, seconds, cancel out, and I'm left with meters, and this cancels out as well. So when I plug this into a calculator, I end up getting 0.00014 meters, or you can write 1.4 times 10 to the negative 4th meters. Now it says that we want it in nanometers, and so to convert this to nanometers, I know that 1 times 10 to the negative 9 meters is equal to 1 nanometer. And so if I have 1.4 times 10 to the negative 4th meters, then 1 times 10 to the negative 9 meters is 1 nanometer. Meters ends up canceling out. I'm left with nanometers, and if you put that into a calculator, or you can do it in your head, that ends up giving you 1.4 times 10 to the 5th meters. And so that's how you work these types of problems. If you need extra help, you can come and get some or ask questions, and I'll try to answer online. Good luck. Keep trying. It will all click eventually. It just takes some practice sometimes. So there is that problem. I don't know how well you can see it. Oh my goodness. I don't know how well you can see it on a computer screen. But on an iPad it looks really, really tiny. All right. Well, good luck.